Good afternoon, everyone. Welcome to intra-process memory protection for applications on ARM and X86 leveraging ELF ABI. You are in the Jasmine Room with your speakers Sergey Brutus, Julian Bangart, and Maxwell Koo. Before we begin, don't forget to stop by the Business Hall located in Bayside A and B during the day for the welcome reception at 5:30 to 7 tonight. The Blackout Arsenal is on the Palm Foyer on level 3. Thank you for putting your phone on vibrate. And with that, here's your speakers.
Hello, it's great to be here. I'm Sergey Brutus. This is Maxwell Koo and Julian Bangart, who, as usual, did all the work. I am a researcher at Dartmouth College. Max is a researcher at NARF Industries. This was sponsored by several sponsors, including the Schweitzer Engineering Labs. Let's get right to the problem. The problem is that if your buggy library gets into your process memory, it can absolutely corrupt anything yes. Aha.
Did you guys really have to try out your ODay?
What? Yeah, hey, Keynote. Keynote.
Oh. Well, I guess we have to start the slides from scratch.
Hey.
Where is your thing?
Okay. Now this is interesting. My entire presentation
your mouse is over here.
Okay. All right. What?
Wait.
What are you doing?
I'm trying to find that.
Yeah. Hey.
Where is it?
Let's start the keynote.
Oh, you can't get to the menu easily.
Here we go. Oh, hey. All right. Yeah, buggy software. That's really a problem. And the specific problem that your standard policies do not protect you from is that anything in your process space owns your entire process space. And so you have the situation when your image parser just stole your private key that was loaded in memory. You could have your SE Linux going, and your process, of course, had to read that file, and it wouldn't help you any because at that point, that key is in memory, and every library can take it over. So then, what are we missing? Software is already split into parts. You already know which parts are supposed to read which things in memory and which they are not supposed to read. Like clearly your image parsing library, your libpng, is not supposed to look at your keys. Clearly your keys are only supposed to be looked at by your crypto functions. And all of that information is already there and the linker sees it. Moreover, the linker knows about all of these interactions. And you can tell a lot by a piece of code, about a piece of code by its interactions. If it looks at your keys, it had better be your crypto library. If it parses your image, it had better be your graphics library. Now, the compiler passes it on to the assembler. The assembler passes it to the linker. They all see those parts of the program. And then a total catastrophe happens when the runtime discards this information. And all of those separate sections get absolutely forgotten. And your runtime is this one big blob. So the prototype we built, which we call the ELF-BAC, and you'll momentarily see why, helps you describe how parts of your application interact and enforce it by way of having your OS loader be unforgetful, not discard this information. Instead, enforce it. So your sections are your types. Your linking is your policy. And you can think of ELF sections as these things that are just a love letter of a compiler to the linker, but in fact there are a lot more, and we're going to argue that. So this is going to be the outline of the talk. First, I will argue for using the LBI as a policy vehicle, and this important key point of having the loader be unforgetful, not discard all of this information. Then we're going to show you what kind of effects this policy produces for OpenSSH vis-a-vis the roaming bug, which hit us recently, and 777, such a Vegas number. Then we're going to talk about another case study that we did for a industrial control system proxy on ARM, which Max has ported our system to from X86. And then we're going to talk about the internals. What do we do to the kernel while we do that? Why it's not something horrible, but rather an extension of an existing pattern that the kernel already uses. So this is a natural extension. So let's talk about the background. What do existing policies give us? Well, SE-Linux is this rather expressive thing that controls access to files. But it doesn't help against things like Heartbleed at all. Because what do you care about files when your target is in memory and your compromised unit of your process is in memory as well? So then you want to separate your parts somehow and prevent the interactions that are not wanted. And you've got a whole lot of work in that direction. Control flow integrity, data flow integrity, software fault isolations, all of those mitigations. Except, as a programmer, you can't tell them anything about what you intend. They derive these things for you. And what is explicit there is lost. Your intent that is explicit in your code by breaking your code into these particular compilation units, that is lost as well. But who remembers that? Who remembered how you decided to split your program? Well, the ELF, the ABI, the binary format, it has plenty of structures that describe the units of your program. And all of this is helpfully passed down to the very point where runtime happens. If you look at your typical ELF file, you've got 30 sections. Every section is semantically distinct and does something special, something that is its intent. And then again, your runtime is totally discarded by your loader and then by your runtime. Let's stop doing that. And so you've got this choice between having some system derive what you intended, say clearly you did not intend jumps into the middle of functions. Clearly you did not intend, as a C programmer, returns to non-call sites and so on. But you also have explicit intents. When you put things as static in the single file, when you put a thing that is not a symbol in that external to the rest of the program in this file, that is your clear intent that this should not be touched by anyone else. This data belongs with this code. And that is very often ignored. There is no way you can defend this at runtime. So you want to describe what matters, and you want to have to describe only what matters. Think of SE-Linux. Does order of operations matter in a process? It sure does. A process is something that unfolds in time. Do memory accesses matter? Yes, because once you've assembled your process, your files are no longer relevant, but you still want your parts to interact the way you want it, not any other way. Instead, you are made to painstakingly describe every file access that your system may ever do. That's a lot of work. That's why in SE-Linux policies, you actually use tools that derive the flows instead of specifying them. The existence of the tools that actually do that is, well, not a good thing. It's actually indictment of that policy approach, right? You should be able to say things that you want, not have to derive them from what you had to say. So what matters? What matters is composition. A process consists of parts. These parts come into play at different times. And they have their exclusive relationships, both in policy, both in sequence. This part comes after this part. We call them phases in our policy. And in data accesses. This is my data. Only I can use that, says a code section, and it shall be so. The first thing we introduce is this idea that sections of code follow in a particular order, and you have this little sequence, your state automaton, that consists of phases. And of course, you can tell in which section you are just looking at your EIP range and seeing in what mapped section of your ELF file you are. And then you want to characterize code by what data it touches, because that's really the intent. Whatever touches your keys had better be your authentication routine. Whatever touches your parser buffers should better be your parser. If something outside of the parser accesses your keys, then accesses your raw input, then you're in trouble. Your parser should not access your keys. Your processing, your session data should not access your raw parser buffers, because that's probably where the exploit is, right? So that observation is going to be very important. And it comes from ELF's standard runtime. So as I said, there are over 30 sections in the modern ELF file. Most of them have to do with startup and runtime loading and linking. So you've got the process linkage table. You've got the global offset table. You've got the constructors, CTORs. You've got the init code that calls them. You've got the destructors, DTORs, and the fini calls that calls them. And you see those arrows on this diagram from John Levin's Linkers and Loaders, just about the only book on the topic. What a shame. And these are the only arrows that are allowed. If your code does something else, you should be killing it, because this is not the intent of these sections. And how would you do that? Well, here's a great inspiration. Let's look at GRSec Pack's UDREF. The intent of the kernel data that it enforces is that the kernel code, all of the kernel code, except for the very few functions, has no business looking at userland data, because userland data can be poisoned by the user after it has been checked by the syscall, and this is how you make the kernel run amok. So UDREF enforces this idea that the kernel code should only touch kernel data, except in very special cases like copy from user, copy to user. We can spread this to userland runtime. Again, enforcing the fact that data and code units have their exclusive relationships. They are meant for each other. If they are cheating on you, having a relationship on the side, then the process is no longer trustworthy. And finally, there is the QMail, which has a pretty damn good security record, where DJ Bernstein undertook to rewrite an MTA, a mail transfer program, isolating everything that could be isolated by splitting it into processes. And the lesson learned was that, as he put it, was that the least privilege was a distraction, but isolation worked. So you should not be obsessive about your policy, enforcing the minimum privilege. This is too much work. But you should be isolating things that are meant to work on other things as much as you can. And so you can imagine a policy like this, where you specify code units and the appropriate data units and their relationships. And if any other arrow ever happens in this graph, you know that you've been pwned and you have to kill the process. So sections are types and linking is policy. What you have there is an observation that what is a type? Well, a type is object with common operations. So if some data takes common operations, then, well, perhaps all that data is of the same type. So methods of a class, type classes, and so on, they express this idea. It turns out that ELF, with its exclusive relationships, expresses this idea as well. But of course, linkers glom things together and loaders forget. And this is what we have to stop them from doing. So the unforgetful loader is a centerpiece of the implementation. So we have to change the page hold handler and the loader in order to spread this information from ELF sections and their relationships to runtime. And this is what Julian and Max are going to talk about. But for now, before we do the demo, we'll talk through the motivating example.
Yeah, and to make it more concrete, let's start off with a small model example. In this case, this would be, for example, how a web application that deals with image files would be set up. When you're writing such an application, you're thinking of, okay, you have libping or some other untrusted code, you might have written it yourself, but it might contain bugs, or you might have a third-party library, and that interacts with some untrusted user input and provides a bitmap file somewhere that the rest of the application can then work on. However, there might be other things in your process, and an attacker will in fact see that besides that user-controlled ping file, there is also going to be an SSL private key for your web server in the same address space. And if the attacker then looks at your ping processing code, finds some funny code patterns, he might send you a special ping file, and then your private key is suddenly no longer quite that private. Or you could have the other use case that, for example, you're running an SSH server and there is a whitelist of authorized keys somewhere in your address space, and a malicious ping file might cause the parser to overwrite that data with something that's not meant to be there, and then an attacker can log into your server. All of these interactions, as Sergey already mentioned, map down nicely to the ABI. We already know in the file formats that we have that there is a region that has the data for libSSL. It's called the .data section in the Linux executable and loadable format, ELF. And existing programming languages like C already make it rather easy for you to split out data into separate new ELF sections. So if you want to express that this is untrusted user input, you could put that particular variable into a dedicated input section and then be able to treat it differently, at least in a linker and loader time. And with our prototype, you'll be able to give it a different policy at runtime as well. And then if we can enforce these policies, then libping will only be able to read the libping input and only write to libping output, and it can no longer touch your private keys, mitigating those vulnerabilities. And now Max will go over some more concrete case studies
Of the actual SSH.
So when we went to look for a program to demonstrate these concepts on, the one that came to mind was OpenSSH in terms of a program where different data accesses might represent different levels of privilege. So OpenSSH has been attacked before with crafted inputs. So the Gobbles pre-auth RCE back in 2002, and then more recently the roaming mode bug in the SSH client, which was an information leak that may disclose your private key. SSH introduced the original privilege drop as a policy primitive, meaning that at a certain point, if the process requests a privileged operation, disallow it and kill it. But access to data outside of what your code should be accessing is also a privilege that needs to be addressed. So more concretely, looking at our policy for OpenSSH, we have 3 different states. We have an initialization state, which touches both the packet processor and the crypto routines for initialization. It then will transfer execution to the packet processing state in order to do things such as key exchange. which will then call into the crypto routines. However, none of these states can directly touch buffers such as where your private key is stored. Only the crypto state can do that, and they can only be accessed through specific call transitions or EIP values. We also split up the heap for each section into separate sections so that your heap data is segregated, addressing issues such as the roaming bug. So we have a quick demo using the POC from the Qualsys write-up of CV 2016-0777. We have a modified OpenSSH client, which uses a simple segregated heap implementation with a bug that large mallocs may overwrite into another adjacent arena, allowing disclosure of the private key. So we have two different binaries, one with an LFAC policy applied and one without. Looking at these segments for the non-LFAC enabled process, you see that there is no special binary segment where we store our policies. Here we run the POC and then run our no LFAC SSH client and connect to the malicious server. We then see that in the output, our private key is leaked. Looking at the LFAC version, we see that there's an additional segment that contains our policy description. Then performing the same step with the LFAC enabled process, we see that the private key is not leaked. An LFAC violation is reported indicating that an access outside of what the policy prescribes has occurred. And examining that address, we see that in the packet processing state, the crypto arena was attempted to be accessed, and it was disallowed, and the process was killed. And there we go. So we've developed policies for both the OpenSSH client and server, splitting up the various concepts between them, the crypto state, the packet processing states, and the overall process control states into separate states and defining transitions between them. We create separate sections for sensitive data blobs, such as the host keys, private keys, that sort of thing, to enable finer-grained access control for data which might be touched by multiple sections, such as the initialization state. This prevents direct leaking of sensitive data like private keys from information disclosure bugs such as this. And again, separate heaps may address portions of what this may have addressed this particular vulnerability, but in general, they would not have they would not have killed the process. They would have allowed it to keep running. They may not have prevented the information disclosure, but not alerted that and disallowed access that occurred.
So let me take over. So think of this as a different kind of a privilege drop. Now, SSH introduced this amazing concept of, if I try to make this privilege call beyond this point, please kill me. I am untrustworthy. You can think of it as a sandboxing, but this is actually policy. This is expression of intent. The same thing goes to touching raw data. Your parser, your exposed parser, is the riskiest part. And it should not be touching anything but raw data and wherever it's putting its well-formed parsed data. So we expanded this concept to a SCADA ICS system. There is a protocol, a rather nasty and complex protocol called DNP3. Chances are it keeps your lights on. This is very popular in the US power industry. And this protocol, the parsers for that protocol have been shown to be extremely vulnerable. There was a talk about how you can take over a master controller device at the control center by Adam Crane and Chris Sistrunk, and that was a pretty major deal. So then, what can you do? Well, you can isolate the parser, and you can have the parser exhaustively inspect your syntax before it lets anything else interact with it. Now, I'm not going to talk about how we structured the parser. You can find this information at the LangSec language theoretic security site at this URL. But the important thing is that we broke the parser out. And then we isolated the parser, knowing that the raw data buffers are likely poison. So your parser is really the only thing that should be touching them. And your parser is only supposed to write into a buffer where it deposits the well-typed parsed objects. And nothing else touches the parsed data. The rest of the code is only allowed to look at the well-typed output of the parser. And we implemented that. We broke the DNP3 proxy out. We put it on this machine. This is an industrial computer. You would find one sitting in a substation. And we fuzzed it. We fuzzed the heck out of it using both American Fuzzy LOP and a specialized parser, fuzzer that was written for the protocol. And it stood up pretty well. If you want to look at those demos, again, look at the URL at the previous slide. And here is the policy. So it was a very simple policy that just isolates the parser from the rest of processing. Next.
So this is a similar diagram to what we showed for OpenSSH, indicating the sections of code and data which each state can touch. Again, we have an initialization state, which controls reading into the input buffer, or writing into the input buffer, I should say, reading from the network, writing into the input buffer. It then transitions state to the DNP3 parsing state, which consumes input from the input buffer and outputs well-formed DNP3 by invoking callbacks in the DNP3 callback state, which takes the well-typed data and reconstructs DNP3 to pass on as a validating proxy.
And so you have your hardened parser protecting the rest of your data, whatever you do with it, which is what you really, really want to have in the device that keeps your light on. We went further and we integrated our patch with the special GR security packs patch for ARM ICS devices. So there is now a GRSec packs version of their patch with coordinated features that are specifically relevant to ICS platforms and excluding some of the features and breaking them out that are not so relevant to these platforms. And we have integrated our patches, tested it, and it worked. So you can, if you're interested in this, there is the URL for that GRSec variant on ARM. And so you see, will this solve all the problems? Possibly not, right? And there is no silver bullet. But now you have an idea what the components of your program are, and it is derived from nothing other than the standard build chain. And if you want to throw in special sections, you can easily do that with a compiler pragma. The linker will happily put those into separate sections, and our unforgetful loader will happily load it. And so, of course, the question is, how did we do that, and what did we have to do to the Linux kernel loader for this for those ACLs between memory regions to take place and be enforceable? And Julian is going to talk about that. And this is going to be a deep dive.
And I'll start the deep dive by going over the various mechanisms that the Linux kernel and, in this case, an X86 CPU use to run a program and set up virtual memory, and then explain where we can hook in to enforce an ELF-back policy neatly. So a program starts off as a set of libraries and object files produced by your compiler that contain different ELF sections. As already mentioned, by default, there'll be sections for code, for data, various helper structures for dynamic loading, dynamic linking, and metadata. But you can add annotations to your program to split off different parts of code and data into their own sections as well. And that way you can pick and choose a granularity for your policy as necessary. Once you have all of your object files and libraries, you pass them off to the linker, which looks at all the sections and groups them very coarsely into segments. So it will take all the different sections you have from every input file, see, okay, here's some that are read-only. It will combine all of these into read-only data. Here's things that are read-write. It'll combine all of these into a regular data segment. And here's all the code. Throw it all together, concatenate it, put it into a text segment, which discards a lot of information. And the only intent that is enforced from all this rich structure that we had before are the 3 read, write, and execute bits. And even that enforcement has only happened in the last 10 years when people started adding the NX bit. When you then want to start your program that you get, if your program was statically linked, it's relatively straightforward. The Linux kernel in the ELF binary format module will read your ELF file, do a little bit of parsing, and look at each of these segments. And for every segment in your binary, it will perform a memmap system call, or the kernel internal version of it, to map that part of the file into your address space. And then it causes the user space to jump into the entry point of your file. If you use any shared libraries, it won't load your program straight away, but it'll load a statically linked helper binary called LDSO, which will parse the ELF file again. And there's another talk about how many fun bugs you can have when those two parses disagree. And the LDSO will do essentially the same thing that the kernel does. That is, it performs one memmap system call for every segment, and then jumps to the entry point. The kernel now represents a process with a structure called task struct, and it has one of these task struct for everything that can execute, that is every thread in your process. And that task struct contains both a copy of the program's execution context, that is, for example, in what signal handler you're in, what registers you have, etc., so that the CPU can switch between different threads. And it contains information about the identity of the process, such as its PID, UID, etc. Because Linux supports multi-threading, different tasks in the kernel can share a single address space. So there is a data structure to represent an address space called an MM struct, and multiple task structs can point to the same MM struct. However, each task can only have a single address space. This address space structure, in turn, points to a linked list of virtual memory area structures. Each VMA struct represents the result of one memory map call, essentially, that was set up earlier by the linker or done by the program at runtime, and contains information about some region of virtual memory and points to the internal file system or whatever other storage Linux uses for what data should live at this particular address and what its permissions should be. Now, linked lists are relatively slow to look up, so there is also an RB tree that indexes into the same structure. And in recent versions of the Linux kernel, there's also an LRU cache to make lookups into the structure even faster. Now, the Intel CPU doesn't know anything about the internals of the Linux kernel. And if you say, OK, here's this tree structure that points to file system pointers, the CPU can't really do anything with that. So there has to be another structure to tell the CPU which particular pages of actual memory in the RAM chips in your computer are going to be mapped to which virtual address. And for that, there's page tables. The page tables also form a tree of fixed depth. Every virtual address is split up into different pieces, and each of these pieces is used to look up the next layer of that particular tree. So you start off with the first 16 bits and a 64-bit processor actually have to be the same, and I'll discard it. The next 9 bits then happen to be an index into the first structure. The next 9 bits after that, which gives you another table. You can use the next 9 bits of your address to look up another entry in that next structure, and so on and so forth, until you finally get the physical memory page that should be mapped to this particular virtual address. Each of these layers also contains provisions for various permissions bits, such as the no execute bit or newer Intel processors, the supervisor mode, execution prevention bits, etc., that allow you to perform some level of policy enforcement on the address space. Now, walking the page tables, every time you would perform a memory read would be very inefficient, because you need to touch physical memory 4 times to look up what physical page an actual virtual address belongs to. And so you would slow down your memory bandwidth by a factor of 5 just by introducing that, which, given that modern processors are already memory constrained, is very inefficient. Therefore, at every single layer of this process, at every layer of page tables, there's a cache. And originally, these caches would be evicted every time you change between processes or address spaces. Nowadays, the processes actually support tagging these caches, so you can have multiple address spaces share the same cache, which allows frequent switching between different page tables.
And this is, of course, a key enabler for us,
Because
otherwise we would not
we'll get to
survive.
it. One important observation is that these caches aren't dumb, but they actually enforce a policy. So the common view is that the NX bit is merely a mitigation, but it actually happens to be a policy that expresses intent. And that policy is checked by the caching mechanism that was originally introduced for performance. Before there was hardware support for the NX bit, some projects such as PAX actually simulated the NX bit because they realized that there's separate caching hierarchies for instruction fetching and data accesses, and that you could desynchronize these caches, which is unintended, but allows you to unintentionally use those caching mechanisms to enforce a policy. And ELFBAC will reuse that trick to enforce data access policies through different TLBs and PCIDs. And that view that everything in the VM layer is really about caching also stretches to the other layers that we have. For example, there is the various layers inside the Linux kernel are all caches of each other. The page table is really a cache of the VMA structs. And each of these layers performs some checks. And of course, these checks get semantically less expressive as you get closer to the hardware. The hardware can only check 3 bits, whereas the kernel page fault handler can perform much more complicated checks. And what we're doing in our ELFBAC prototype is we're just adding another layer of caching in between and using that caching to enforce our policy. For example, when you have a page fault, that is when you try to access some page and somewhere along that hierarchy of page tables, there's a bit set that says, okay, don't continue here. The CPU will raise a page fault. And the kernel will then look up the VM area struct that I already mentioned earlier to find out whether the access is allowed or not and what physical memory page it should map this to. And here it inserts a semantic policy check. If that virtual memory address is invalid, it will send your process a segmentation violation and kill it. Similarly, over the time, the Linux kernel has acquired many different features that are added in and hooked in on this page fault handler, such as swapping in and out memory, implementing copy and write, and growing stacks and heaps. ELFBAC changes the data model that I mentioned earlier, where there is an end-to-one relationship between tasks and address spaces to an end-to-M relationship. So suddenly a task can have different address spaces depending on what particular phase of execution it's in. And ordinarily, because this is a data structure that's very central to the Linux kernel, a lot of different kernel code and a lot of drivers would have to be changed to update all of these M copies. However, if you think of ELFBAC as just another caching layer, we don't have to modify the rest of the kernel. The observation is that each of the different address spaces for different phases of execution of our program are going to be subsets of the same original address space that the programmer has in mind when they're writing. So we can keep all the original data structures intact and represent that base address space with the existing MM structs. And if you squint enough, those different subsets that we actually want to enforce act a little bit like a cache. And now we only need invalidation of these caching layers instead of the ability to mutate all these different address spaces as we move through execution of our process. And because there is already a complicated hierarchy of caching, and that has changed a lot while Linux was under development, there is a flexible API in the Linux kernel called the Notifier plugin API that allows you to hook in custom invalidation mechanisms for different caches. We use that and instrument the page fault handler to then enforce our policies. When we encounter a page fault in a process that is using elfback, we first look at the original page tables that the rest of the kernel still maintains for us and see if it would have caused a fault there, in which case you're actually doing something else and you should do, and we'll pass it off to the old page fault handler to, for example, swap in your process or perform copy or write, etc. If that other page fault handler then performs any changes to the page tables, which it usually does, it will send an notifier update to us, and we'll in turn invalidate our cached page tables and then allow the user space process to resume execution, and the next time, hopefully, that access should not fail. If, however, the memory access that this particular phase of execution would have been a valid access if we hadn't been running elfback, then something is happening that we want to catch with our policy. And we look up our elfback policy data structure. If necessary, move our process to a different phase of execution. So for example, if we detect that you just jumped into code that belongs to a different library, if your parser is done and is now invoking some callback, we'll move to that different address space. If we find out that the access wouldn't cause any change to the policy state that we're currently in, but should be allowed, then we'll copy the page table entry from the original base address space into the one that's currently loaded in the processor. So there's different task structures that still point to the original Linux kernel memory space, which the rest of the kernel sees. So we don't have to touch most of the kernel. We don't have to touch the millions of drivers that are in Linux. Whereas only the elfback layer sees that there is this additional caching layer, and there's an elfback policy, and we actually have different structs for each thread, and each thread can have multiple structs. And these correspond to their own page tables, which are actually loaded into the processor. And we use the Notifier API to keep those in sync. On our X86 prototype that we have, our proof of concept implementation, we built multiple benchmarks. We built an Nginx benchmark, and we built a synthetic benchmark that simulates the motivating example that we had earlier, that you decode some images, perform some processing on it, and then re-encode them as ping. On those benchmarks, we usually found a performance overhead of about 5% on AMD processors. However, on Intel processors, which have a more sophisticated TLB caching hierarchy, we found significantly worse performance overheads of up to 30%. Part of this is because our benchmarks are CPU bound, and we exercise that switching between address spaces quite a bit, and some of the data structures we're using the kernel, etc., could be significantly optimized, for example, for cache behavior. One interesting fact we found is that when you're already running under another virtualization layer, performance overhead was only about 15%. That's because virtualization layers already affect virtual memory, and people seem to be willing to take that performance hit. And virtual memory hypervisors already provide more efficient means of switching between different processes and try to optimize virtual memory handling, lowering our performance overhead somewhat.
So I should say that on ARM, we had a much better deal because, in fact, we wrote our program to be sparing with its context switches and its phase switches. And so unlike Nginx, which was written with a completely different idea in mind, we had negligible performance loss. So it really depends on how you plan your code. But if you co-design it with the idea that you want to runtime separate its components and enforce that this code owns this data and only this data and vice versa, then you can get away with very small performance overhead.
And yes, besides the performance tuning opportunities that I already mentioned, one missing feature of the x86 prototype is that it currently is a bit clumsy to use with dynamically allocated memory. But that's mostly a user space issue in that we would need an elf-back-aware malloc that puts dynamically allocated objects into the right sections automatically without you having to implement your own memory allocator. And there's ripe opportunities to integrate it with other system call policy mechanisms like SE-Linux and Capsicum so that the rest of your security mechanisms know what is actually going on inside your process. And a neat feature of ELF-back is that these policies that you write can compose. So someone who is writing a library can also provide an ELF-back policy that says, okay, these are the things it should access. And of course, it's outstanding to write policies for many popular libraries. And now off to Max to talk a little bit about ARM implementation.
Yeah, I'll quickly just go over the differences between the ARM implementation and the x86 one. They're fairly minimal. They have similar hook points in the page fault handler. In the ARM implementation, it was more geared towards embedded systems, so we focus more on the static linking case than the x86 one. The dynamic linking case could be supported by providing a modified ld.so. We created tools that generate custom linker scripts and packed binary policies that we load into a special segment that are parsed by the bin format elf loader inside the kernel. Again, the page fault handler modifications are pretty much the same. We don't have an struct per state, though. We just copy the page tables, which simplifies some of the synchronization between VMAs and such in each struct. And we use ARM's ACID support on supported platforms to be similar to the PCID tag TLB support in x86 to give us a performance boost.
And so to wrap up, who cares? Well, every programmer who uses C and C++ static scoping to separate data from the rest of the program does care. And we should note that C++ took over the world by making enforceable contracts. So this is your opportunity, by writing in this style, to create contracts between the parts of your application, between the parts of your address space that are enforceable at runtime. And this is no mean thing. And then, of course, there are different ways to separate the parts of your program, but only those that are enforceable matter. And, we are opening the way, we believe, to make these separations matter. These separations are well understood, and now they can be enforced. And that's really the takeaway. So your per process bag of permissions is no longer a suitable policy with the software being composed of so many parts and none of those relationships being respected or enforced at runtime. Instead, all of that information is available through the ABI. So we just need to tweak the loader to pass it on and to make the information from the ELF structures available to your structs. Then you can enforce it. And then you can provide just enough granularity that way to capture your intent, to capture these special exclusive relationships between your code components and your data components. And this is the sweet spot, and would like you to use it. And it's on GitHub. Thank you. Questions?
Okay, so I have a question. I'm also working on the ELF sections, and while I was looking at the ELF section or the VMAs, I find there are many virtual machine areas that is anonymous. There is no backing file, and it is not described in the ELF binaries. So do you take care of these anonymous regions or ranges?
Yeah, that's correct. So those are the dynamically allocated memory. What you can do with them is that you can tag them at runtime by using a special malloc. This is what we do with our ARM port with the ICS proxy. Or you could also derive it in different ways. Yeah, I mean, where do labels come from? You need some rules for labeling them. You can guess them, or you can explicitly specify them. It's not hard. Any modern allocator allows you to allocate from a specific arena. So you can have that arena labeled if you care to control the dynamic anonymous mappings as well.
Okay, thank you.
Yeah, I have a question.
More questions?
I actually like what you guys have presented, but when a application is being attacked, it is possible to do the system call to change the, the NX setting to make it, say, a part of the heap writable. So how do you? I mean, that doesn't seem like you could prevent that.
Well, so we filter system calls. We have functionality for filtering system calls in a particular process stage to the mask that is allowed for that phase. We did not dwell on it in the presentation because this is, people have done that, right? This is your basic sandbox.
Okay, thank you.
But what people have not done is try to express the memory ACLs between the parts of a program, between the notional parts of the program in policy. That we consider our biggest contribution.
Hello, I also had another question. Thanks for the talk, it was really interesting.
I'm sorry to interrupt really quickly. We're going to have to clear, get these gentlemen off stage. So we're going to take them outside on the side. So any additional questions, if you want to catch them right here on the side, that'd be perfect. Sorry about that. Thank you.
Yeah, thank you again.